In this video, we're going to introduce the European research project, SuperMaMa. The project acronym stands for Superconducting Mass Spectrometry and Molecular Analysis. The SuperMaMa Consortium is a collaboration of 5 research groups in 3 European countries, with expertise in quantum physics, low-temperature electronics, synthetic and photochemistry, mass spectrometry, and the analysis of complex biomolecules. How do we do this and why this is important is what we are going to explain in this video. Challenge 1: Mass spectrometry of massive biomolecules. Mass spectrometry is a well-established method to determine the abundance of atoms and molecules in unknown samples, since many molecules have a uniquely defined mass. Mass analysis has become an essential tool in physics and chemistry, pharmacology and biology, and even in applications of archaeology, environmental sciences, or criminology. The global market for mass spectrometry amounted to about 5.5 billion euros in 2020 and is expected to double within the next 10 years. Modern mass spectrometry usually relies on 3 pillars. Mass spectrometry requires isolating and charging molecules. Both challenges are generally solved by matrix-assisted laser desorption, MALDI, or electrospray ionization, ESI, 2 techniques that became so important that Kiyoshi Tanaka and John Fenn were awarded a Nobel Prize in Chemistry for these developments. It then requires sorting the molecules by their mass-to-charge ratio. For pulsed samples, this is often done by time-of-flight analysis, or most precisely in ion traps. For more continuous beams, this is best realized by quadrupole mass filters. However, for continuous beams of very massive ions, precise filters have still been missing. MS Vision in Almere is developing quadrupole technologies that will provide good mass resolution for singly charged proteins in a new mass regime. Finally, the molecular ions need to be detected. But wait. This will be explained in our challenge number 3. Challenge 2: Protein functionalization and single photon chemistry. You have already heard that ESI and MALDI can provide charged molecules flying in air or vacuum. However, manipulating the molecular charge in free flight has remained an outstanding challenge in the scientific community. And yet, it is essential if we want to analyze protein properties such as their folding, their vibrational or electronic properties, also as a function of their charge. Neutral, isolated biomolecules in high vacuum are an entire class of matter that has evaded scientific analysis so far. In collaboration between the universities of Basel and Vienna, we ask, can we modify proteins such that they cleave off a well-defined charge group when they absorb a single quantum of light? Would that even work in high vacuum? Can we develop chemical tag to universally neutralize and reionize protein beams in flight with only minimal perturbation of the protein itself? Can we generalize these ideas for mass spectrometry and molecular beam analysis? While many ideas of protein functionalization and dissociation has a long history in chemistry, photochemistry of tagged proteins is still a wide open field of research. Challenge 3: Superconducting quantum detectors. Many conventional mass spectrometers eventually detect large molecules by accelerating them to speeds beyond 20,000 meters per second, 4 times faster than the Apollo 11 rocket. Beyond this enormous speed, the impacting molecules can trigger an avalanche of secondary electrons in an electron multiplier and generate a measurable current pulse that lasts only a billionth of a second. However, if we want to analyze slow and possibly even neutral proteins, how can they be detected if they have 100 or 1,000 times less kinetic energy than required for conventional detectors? Quantum technologies are the solution. Single Quantum in Delft is developing novel detector arrays where each pixel is a single superconducting nanowire of only 100 nanometer width and 10 nanometer thickness folded into a meander that measures only 20 micrometer across. When operated at a temperature below 4 Kelvin, the wire is well superconducting and carries current without any loss or voltage drop. However, this quantum property can be destroyed easily and fast when the wire absorbs the energy of even a single quantum of light, a photon. This change of state increases the resistance of the wire within picoseconds and generates an ultra-fast voltage signal that can be amplified and detected. Such superconducting nanowire detectors, SNWD, are currently explored at the University of Vienna as detectors for single atoms and single macromolecules, where they're trying to understand the energy threshold, the role of their internal structure and energy, all of which should be much more favorable than conventional classical detectors. Challenge 4. Cold integrated electronics for quantum detectors. If a single quantum detector is already great progress, how much better would it be to have many of them? A genuine nanowire camera should enable novel applications in molecular beam detection, profiling, and deflectometry, but of course, also generate new research in photonics or infrared imaging. While Single Quantum is developing methods to scale their arrays up to new limits, the partners at EPFL Neuchâtel are complementing this development with forefront research on integrated cryogenic electronics. Since each detector pixel should be controlled individually, the number of control and signal wires could be vary in a multi-pixel detector. However, the whole device has to be cooled to 3 Kelvin, that's about minus 270 degrees Celsius. This is hardly compatible with many wires going in and out, which act like highways for heat transport. It would also be incompatible with conventional detectors, which generate more heat than the cooling power of available fridges. A solution to this challenge is the development of cryogenic electronics, which restricts the room temperature connections to a few input wires, while all signal conditional and processing is performed at low energy and at the low temperature of the detector chip itself. Designing transistors, capacitors, and resistors at low temperature requires sophisticated modeling of changes in their mobility, electrical leakage, and other parasitic effect. In most cases, they run faster, with lower noise and energy consumption in this cold environment. It makes them more compact, more performant, and better suited for time-resolved measurements. While within the SuperMaMa project, we are focusing on realizing a 128-pixel prototype. The dream is that nanowire detectors and integrated electronics can eventually be massively parallelized to capture fast phenomena in photonics and mass spectrometry accurately and across large areas or with excellent spatial resolution. Realization of the SuperMaMa machine and experiment. All of these tasks are complex. SuperMaMa combines the best methods, ideas, and technologies from all project partners into a single instrument. This machine has already taken shape at the University of Vienna, combining new avenues in biomolecular synthesis and functionalization, biomolecular beam preparation and mass spectrometry, high-power, fast, and ultra-fast lasers for photochemistry, quantum detector arrays with growing pixel numbers, integrated cryogenic low-noise electronics. This is the beginning of new adventures in the exploration of single photon chemistry, with functionalized made peptides and proteins in the detection of mass-selected, charge-controlled proteins and new applications of a quantum detector camera.